in 2 hours offered to you by Owtana Tech regarding their energy management. To achieve the goals for the 2050, the total power installed should reach globally 18,000 gigawatt, so more than 6 times the current power installed. In this picture, we can see the share globally of the different sources. In light green, there's the solar, and as you can see, is roughly the 10%. But this percent is increasing year by year. Here are some data. As I said before, there are differences in different countries. So you can see Russia has only 1% of share of wind and solar power, while EU has like 30%. But globally, the share of solar energy is increasing without exception. Solar photovoltaic system will produce 35 to 40% of the global electricity production in 2050. So, what's the key point that you have to understand? That this kind of technology is the future in every part of the world. So it's a big market with big investment. Now we can pass to an introduction to the solar energy. The total solar power incident on the top of the atmosphere is approximately 173,000 terawatt. Just to give you an idea, global primary energy consumption is roughly 20 terawatt per second. So the total solar power that is reaching the Earth is different order of magnitude higher than the energy that the planet needs. So it is an important source, but for sure there are different losses that cannot let us exploit all this power. And now we will see what kind of losses. For example, we can see an image. There's the 30% of the power that comes from the sun that is reflected back into the space. This 30% is called albedo. Albedo, that is technically the percent of light that is reflected by a surface, in this case the atmosphere. Another 23% of solar power is absorbed by the atmosphere, by ozone, CO2, and H2O. If we sum these two components, we can understand that more than 50% of the solar power is not exploitable because it not reach the Earth. But 48% is absorbed by ocean and land. However, not all the solar power absorbed is exploitable. In fact, 71% of the sunlight is the ocean, and not all the land is available to install photovoltaic panels. You can understand, for sure, we cannot install solar panels in forests or in steep mountains. We can install on the roofs of the houses, for sure, on the car parkings, for example, they are more used, but not all the land is available to install photovoltaic panels. But, all considered, the light left at our disposal carries a total power of roughly 5,000 terawatt. That is a lot. To understand why part of this energy is wasted, we have to understand how the solar ray is composed. So we need to study the solar electromagnetic spectrum. We are not going to go in details, but just to understand why part of the heat that is coming from the sun is wasted. So, how is composed the solar electromagnetic spectrum? There are three components. Ultraviolet, that has high energy, but is a low quantity of the solar spectrum. There are wavelength, we can see maybe better here in the image, lower than 400 nanometers. After that, there is the visible light, that is our sweet spot, the best spot, with wavelength that goes from 400 nanometers to 700 nanometers. This band contains the highest density of photons with the exact energy levels needed to match the atomic structure of semiconductor materials. What does it mean? That the part of the visible light is the part that we can better exploit to absorb energy. Because the ultraviolet has too high energy, and we will see why later. And instead, the visible light has the better. The last part, the infrared, has low energy, too low energy, but it represents the highest part of the solar spectrum with 52%. And this part has wavelength higher than 700 nanometers. We have an image. So, as you can see, the visible spectrum is only a small part of the entire wavelength. So, this concept will return in the next topic, that is the working principle of the photovoltaic cell. So, let's make a step back. We will remind how a semiconductor behaves to understand how the cell is working. So, the main material that the cell is made of is silicon. Silicon has a crystal structure and is tetravalent. What is meaning? That in the external energy level, it has only 4 electrons. I remind you that to be completed, an external level of the atom needs 8 electrons. So, from the solid-state physics, the solar or photovoltaic PV cell is the basic element of the PV systems, because the direct conversion of sunlight into electricity occurs inside. So, thanks to the cell, we can change the solar energy in electricity. The conversion efficiency is achieved by exploiting the properties of semiconductors, as we will see. And here on the right, we have an image of silicon. Why it is important? I explain it to you in simple terms, and later we will see the technicalities. Thanks to the solar energy, we can stimulate the electrons of silicon or other atoms, as we will see, and we can pass these electrons from the valence band, that is the band that normally occupy the electrons, to the conduction band. And to do that, we need energy, a precise amount of energy. So let's repass what are the band. Valence band composed of the pair of electrons involved in chemical bonding, that are the point that you see in the images on the right. The conduction band, composed of the electrons with an energy level higher than the previous, to permit their motion in the crystal lattice. So, if the electrons have enough energy, they can go to the conduction band and moving in the crystalline lattice. Between the valence band and the conduction band, there is the band gap, that is an energy gap. And it represents the energy jump required by the electron to move from the valence band to the conduction band. it depends on temperature. So T in this slide is for temperature in Kelvin. Why it depends on temperature? Because of course, as you know, higher the temperature, higher the energy in the system. So lower it will be the energy that we need to put into the system from the external. In order to obtain the diode operation, unidirectional switch, a positive negative PN stay per positive and negative homojunction is built. One crystal is doped with trivalent atoms, for example, boron with 5 electrons, and the other one is doped with pentavalent atoms, phosphorus. So, what are we doing? In the cell, we create, as you can see here, a p-n junction. N negative is the one with more electrons, so it is made of phosphorus and silicon, while p stay per positive, and they are made of boron and silicon. We can exploit the difference in electron concentration to create a difference in potential, the voltage that we need to create current. Okay. So, in the p-type crystal, the majority carriers are holes, acceptors, while in the n-type crystal, the majority carriers are electrons, donors. Thermal energy causes a small fraction of the covalent electrons to break loose and become conduction electrons. So, you can see here in the images, there are two kinds of current. Field current is the current that we can exploit to obtain energy. So, is the current caused by the difference of potential between the P junction and the N junction. But what's the problem? After a certain amount of time, a lot of electrons switch from the p-type to the n-type, because different concentration, in case of different concentration, the electrons tend to re-equilibrate this disequilibrium. So we have two currents. When the two currents are equal, the system stops working. I know that at the beginning it can sound a little bit confusing, but I promise you that it will be clear at the end of the course. So, at the interface, that are where the two junctions are connected, electrons of the n-type crystal diffuse to the p-type crystal, forming a depletion region, with no mobile carriers. When the current oriented by the electric field counterbalance the diffusion, the process stops. So, when E diffusion is equal to field current or photovoltaic current, the system stops working. The field current is due to minority carriers, electrons in p-type and also in n-type. The key point to remember is that the junction acts as a rectifier. So, why before we saw the solar spectrum? Because only the photons with enough energy create electron-hole pairs. These are the pairs that we need to exploit to produce differential potential and so current. Here's an equation. You don't need to remind that, but just to understand. The photovoltaic energy is equal to H, that represents the Planck constant, so it's a natural constant, you don't need to remember, multiplied by the frequency. Frequency that is equal to the speed of light, c, with respect of the wavelength, lambda. So, as we have seen before, I just take the image. This is the wavelength. So only photons with enough energy can go to the conduction band. If you remember, we said that the visible light is the sweet spot, the best wavelength that allow us, and we can come back to this slide, to create electron-hole pairs. So please remember why we cannot exploit all the solar power. We have seen because of part is absorbed in atmosphere, part is reflected, part is wasted in the ocean, but there's a natural, a physical limit of efficiency that is caused by this phenomenon. So I think that is clear. In the presence of the electric field at the junction, electrons are attracted towards the n-type layer and the holes toward the p layer. This charge motion, intrinsically equivalent to reverse current, is the source of the photovoltaic current. Hence, inside a solar cell, an open circuit, the photovoltaic current induces a reduction of the electric field with a consequent steep increment of the diffusion current. Finally, at open circuit, the two current contributions are counterbalanced. Here is a graphical representation of what we have just said. There's lambda max is a theoretical limit. So it's not a problem of technology. We, university, studied the best material to achieve the higher efficiency, but there are limits that cannot be passed, and this is a theoretical limit. There are also other kinds of losses that are less important, but as a certain amount of losses. These losses are caused by not all incident photons pass through the cell. Part of photons is reflected. So the surface of the cell not absorbs all the solar energy. Part is reflected, and this causes a loss. Some electron-hole pairs recombine themselves before they are separated by the electric field inside the junction. What does it mean? That instead of passing from the N junction to the P junction, some electrons remain in their junction and not allow us to create a different potential, so they recombine. There are also the resistance from the frontal electrode of the cell that is used to pass the current to the circuit, and the resistance due to the four lateral surfaces, because, of course, the cell is not infinite. At the end of the cell, there is air, and this causes some losses called lateral, because of the lateral surfaces. But we will see it better later, I promise. Here is the configuration of real solar cell. I can use these moments to remind you that if you want to take the exam to obtain the exam certification, we will also give you some materials, the slide of these courses and other materials, to study these topics better and to attend the exam successfully. So I remind you this possibility. Let's come back to the configuration of real solar cell. So, as we have discussed, there is the p-n junction, p layer, n layer. There is the front contact, there is the back contact, and there is the bus bars. They are used to pass the electricity. Here are the dimensions, if you are interested, of the cell. I want only to underline that each cell is obtained by wafer of 100 to 250 micrometers. So really thin, really thin. Okay, this is a key point to understand how a photovoltaic cell works. And this is the IV curve, or current voltage curve. That evidence the correlation that is between the voltage, so potential difference, with the current. This curve that you can see on the right is the curve under dark condition, so without sunlight. For a solar cell, the photovoltaic current is proportional to G. What is G? G is irradiance. It's expressed in watt per square meter. Then it tells us how much of the solar energy is coming, okay, in simple terms. And oriented by the junction electric field. Photovoltaic current is equivalent to a forward bias. The diffusion current, in opposite direction, is strongly increased if voltage exceeds a threshold. Up to the balance value, UOC is open circuit condition. So, what this slide is saying? It's saying that there's a correlation between voltage and current for a cell that is always the same. So, for 4 ampere, there is 2.5 volt. And after that, it is not possible to create energy. There is failure. So the limit condition, represented in the curve, is the value of the voltage in open circuit. So with the switch that is open circuit condition. Under the sunlight, instead, we have this kind of curve in blue, that if you pay attention, it is the same curve, but down. So we can take the curve under dark condition and have the curve under sunlight condition. In, I think it's purple here, there are the power curve that tells us which is the best point in which we can operate. So, of course, from our system, we can achieve the maximum power possible, maximum level of current that correspond to a certain maximum value of voltage. Our aim is to stay in this configuration of maximum power. A good model to analyze the behavior of a photovoltaic cell is represented by the 5-parameter circuit. That is that one in the image. This is an example. There are other kind of model that are more simple or more precise, but these represent the most important parameters. So, for example, we before talk about recombination. This circuit do not comprehend recombination, but it is a minor source of losses, so we can neglecting for the aim of this course. So the 5 parameters are the photovoltaic current and the diffusion current that we have seen before, the shunt resistance, the series resistance, and the junction quality factor. There are the new factors that we are studying. What represents these symbols? The shunt resistance represents the losses caused by the lateral surface, so it could be modified by increasing the isolation of surfaces. For sure, if we increase the isolation of the surfaces, the shunt resistance decreases. And with a lower resistance, we can increase the current. The series resistance represents the losses caused by the busbars and the front contacts. Can be modified by changing the number of busbars. So what's the problem here? That depending on the current, we need a certain number of contacts and busbars to pass the current to the house or to the grid. But these contacts and these busbars represent an inevitable cause of losses. Let's see the parameters of the IV curve. The IV curve of an irradiated cell is nonlinear and exhibits these remarkable points: the maximum power point current, maximum power point voltage, short circuit current, and open circuit voltage. What do you have to remember? You have to remember that there are certain points called maximum power point current and maximum power point voltage that represent the ideal working condition. So we can extract the maximum amount of power. And there are two parameters that show us where the failure occurs. So if we achieve short circuit current or open circuit voltage, we achieve failure. So the system doesn't work. So we for sure we have to avoid it. Okay. The power output from a PV cell has a maximum at maximum power point current and maximum power point voltage, while the power output is 0 at short circuit and open circuit condition. The fill factor is a useful parameter to compare the performance of cell. Typical values for crystalline silicon are 0.7, 0.8, while for amorphous silicon are 0.5, 0.6. What's that? To compare cells made of different materials, for example, monosilicon, polysilicon, or amorphous silicon, we can use this fill factor. It's just a curiosity. It's just useful if you have to choose the better technology. But we will see this in the design phase later. Let's see the dependence on irradiation. The IV curve of a solar cell changes due to irradiance variation. Short circuit current and maximum power point current change roughly in proportion with the incident irradiance, while the voltage, both open circuit and maximum power point voltage, have minor variations due to a well-known logarithmic law. So, again, in simple terms, what's the difference between current and voltage related to the irradiation? That an increase in irradiation has a bigger effect on the current with respect to the voltage. So, as you can see in the graph, with higher irradiance, there are higher current, but a lower increase of voltage. And this is useful. So, our the irradiation, our the power that we can extract. But there's a limit for the voltage, because the dependence that you can see in the equation below is a logarithmic kind. Here we are on normal operating cell temperature. That is a project temperature that is useful if you have to choose your panel to understand how much power you can extract. Let's see what it is. The normal operating cell temperature is the equilibrium temperature of solar cell inside a module exposed to the sun in standardized conditions. Typical values are 43 to 48 Celsius degree for freestanding installation. Of course, if you want to buy a solar panel, you need the data from the panels. And to compare panels from different companies, you need a standard parameter. So you can say, okay, under the same condition, these different panels give different power output, current output, voltage output. Okay, and one of the parameters is usually the normal operating cell temperature. Here you can see the standard condition. What does it mean? There are irradiance of 800 watt per meter squared, an ambient temperature of 20 Celsius degree, and wind speed of 1 meter per second. Why it is important, the wind speed? Because wind speed could heating down the solar panel. So we can see later, temperature has for sure a good effect on the power output, but only until a certain point. Because after a certain point, the losses with the temperature are higher with respect to the power increasing. So that's why there's also the wind speed. Because with different wind speed, we could achieve more power with higher temperature, because the wind is cooling down the panels. It's like, I don't know, the PC that need refrigeration. It's the same thing. The wind cooling down the surface of the cell. So let's call about mismatch. Mismatch is another key factor in making a panel. What is mismatch? When you see a solar panel, I can search for an image just to let you understand. Okay. You can see there are different solar cells. It is the little square in blue, connected in series or in parallel. Okay. Because, as we have seen, the power of a single cell is too low to be useful in a house or for industrial sectors. So we need to connect them. But in doing so, there's the possibility that one cell maybe is under shadow or has some kind of problem because of manufacture, or because it reached failure, or for every reason. Maybe one cell has problem while the other are working normally. What's happened at the whole panel? That's what we'll try to understand. So let's come back. Okay, at the concept of mismatch. So the loads require voltage and current higher than those given by single cell to achieve the required power. So it is necessary to connect several cells in series and or in parallel, as we have seen. If a certain number of cells, n represent a certain number, are connected, and one has the EV curve different from the other curves, mismatch due to manufacturing tolerance defect, curve A, or partial shading, A prime, the equivalent IV curve, represented by the curves C and C prime, is obtained by the sum for each value of current of the voltage. That is, number of cell minus 1, that is the one with the defect, of the good cells, dashed curve B with the voltage of the weak cell A. It could seem a little bit confusing, but let me explain. You can see in black with a continuous line the IV curve in normal condition, and the tars C, and the condition with defects, that is A. With the manufacturer defects, we have the IV curve A prime. Also, sorry, the C prime for the manufacturer defects, and the A prime for shadowing. So, if we have shadow, the curve A prime shows us the behavior of the cell that is put under shadow condition. And A prime is the IV curve of the entire solar panel. So, what I need that you understand, that because of a single cell, the entire IV curve, so the entire power output of the solar panel, is strongly reduced. So if we do nothing, only a small amount of shadow could shut down the entire panel and produce low to a null energy. So this is the graph. But the key concept to have in mind is that shadow or defects due to a bad fabrication could cause serious problem to the panel. So cells in monosilicon with high shunt resistance, the current produced is equal of the current produced by the weak cell. So it is not important that, I don't know, 9 cells in series are working correctly if the 10th cell is under shadow, because the equivalent current is equal to the current of the cell under shadow condition. Okay. So the most important result is that Pmax is much lower than the expected power. If the current required by the external load to the PV cells is higher than the short circuit current of the abnormal cell, it operates as a load with reverse voltage. This is the worst scenario. So the cell that is not working not only produce few current, but it also acts as a load. So it reduces fundamentally the power output. Okay, I think that the concept is clear. We can maybe skip this part. Okay, just the weakest cell is forced to absorb power higher than its thermal limit with hotspot, which can cause failure. What does the meaning? There is the case of failure because one cell, what is the hotspot? An hotspot is a case where a cell has overachieved its temperature range. So the temperature is increased so high that the material failed, and that's the hotspot. So if the voltage of the good cell exceeds the breakdown voltage, it occurs the immediate failure of the shaded cell. What's our solution? Our solution is a bypass diode. A diode in parallel with the shaded cells avoid that the cell operates as a load with high reverse voltage. So what's happening? Basically, we are skipping this cell. The current pass through the diode and avoid passing through the weakest cell. So our power output is, of course, reduced with respect to the normal condition, normal operation, because we have a cell less. So if the panel has a row with 10 cells and one is, for every reason, shadow, manufacturer tolerance, or hotspot is weak, we can bypass that with a bypass diode to achieve a level of power that is acceptable. So if I expect to have 20 watt power in the output, with a bypass diode, I can obtain maybe 18, 19, not 20, but anyway, a good value. While if I don't put a bypass diode, I will obtain maybe 3 watt, 4 watt. That, with respect of 20, is not acceptable. I cannot work in this condition. Okay? In the figure on the right, where the cells are represented by current sources, only one bypass diode is displayed. Nevertheless, such a protection technique for every cell is too expensive in practice. The diode is connected in parallel with a group of serial cells, 18, 24, 36, within a PV module. So, what these slides are telling us? That, for sure, the optimal case will be having a bypass diode for each cell. But bypass diode has a cost. So, we cannot you know, if you have a solar field, you have a certain amount of panels, 15, 20, depends on what you need. And if you have to put for 20 panels that, as we will see later, as 100 cells, you have to buy 1000 bypass diode, and it is not economically sustainable. Okay, so we use an intermediate solution, that is to put a bypass diode at the end of every row, so a series cell, 18, 24 cell. A similar comment can be made for the parallel connection. Okay, I'm reading the questions, but I don't know if you listened before at the beginning of our meeting. I will answer all the questions that you correctly put in the chat at the end of the lecture. Or maybe I can make a little pause before we end the first meeting, because I remind you that at a certain point we have to pass to another link of Google Meet. I can answer that. So I read your question. Thank you. Please feel free to ask every question, every doubts. There are no stupid questions. So please. So come back. A similar comment this I said. But for the aim of this course connection, you have to remember that it is necessary to use cell with IV curves as close as possible. That requires an accurate selection of the cells in the manufacturing sorting. As an example, only the cells with identical values of short circuit current, open circuit voltage, and max power are connected nevertheless. In the overall PV array or field, a loss due to production mismatch of IV curves is around 2 to 4%. So, from the production side, we received cells that are not perfect equals. And we connect these cells. So, this causes a little losses, about 2%. Even if an accurate selection of the cell according to the IV curves is performed, during the plant operation, it's not possible to avoid the IV mismatch due to external reason, for example, the shading effect, as we have seen. Okay, so the next is another important section of our course, so we can make a little pause to answer the question that I see. Again, I remember you that you will obtain a certificate for attending this course for free, but you can also obtain a certificate that attests that you passed an oral exam, but the second certificate has a cost 10 to 15 euros and 1.5 million taman. I hope to pronounce it correctly. But we will give you this information on the website, on the group chat, on the Telegram chat, so no worries. And you can contact me, of course, for this kind of information. So let's read the questions. Could we derive any rough estimation of how the shadowing affects? For example, could we estimate that 1 out of 30 cells under the shadow could cause up to 80% loss of the total power generated? Okay, so you want an estimation. Yeah, you are quite right. You are quite right. If we can come back, okay, to this graph, okay, you can see that when we have maximum power, so black condition, this question was made by Majid. I hope to pronounce it correctly. And the condition of max power, if you go down to the blue line, that is the line due to shadowing, you can see that the current is much lower. So your estimation of 80% loss is correct. But remember, this is the case without bypass diode. So for sure, in the system that are currently working, this kind of losses should not exist. Okay, so if we don't put bypass diode, yes, the losses could go up to 80% of the power generated. But fortunately, we have a solution that causes little losses, like 5%, 10%. But depends also on the number of cells that are under shadow. If there are only a low angle and there are 3-4 cells that are under shadow, not a great loss, like 10% maximum. But if all the panel, all the biggest part of the panels is under shadow, of course, our losses are higher. Okay, I read in the group chat that we can continue the class using the same link, and there is no time limitation. That's perfect. Okay, so please do not leave the class. We can continue here. No worries, Majid. And there was another question, and later we can come back to the course. Will we have more energy the closer we move solar panels to the sun? Can we expect that in the future we might actually take solar panels into the space? Okay, this is an interesting question, and I can answer that by saying that the problem with we move solar panels to the sun. Of course, if you're talking about, I don't know, put the panels in the ground or in the last floor of the Empire State Building, for example, this not make much difference, So put the panels at 10 meters or 100 meters, make zero difference. If we put in the space, yeah, for sure, as we have seen, you can avoid the losses due to reflection, due to albedo, due to the atmosphere. But you have another problem, that is how to transport the energy from the space, that is where you put the solar panels, to the Earth. And this is a big problem, I can promise you. There is a problem of technology, for sure. I'm not an expert on that kind of research, but it is, of course, also an economic problem, because you have to think, sometimes you can listen to someone that say, it is enough to put a lot of panels in the Sahara Desert, and we can give energy to all the world. But what's missing? What's the people that are not into this kind of world are missing? That the connection has an important cost. The cables that you need to connect the solar panels to your building, your grids, has important cost and also have losses. So if you have a cable that is long 100 kilometers, you have important kind of losses. Okay, so your idea is interesting, but I don't think in the near future it is possible. I hope you understand why. Okay, perfect. So we can go on with the next part, that are photovoltaic systems, components, and designing. The solar panels alone cannot bring you energy, so we need other components. The other components are inverter, maximum power point tracker, raking structure, and optional a battery storage. Briefly, the inverter, it is used to convert the direct current that comes from the solar panel to alternate current, that is the current that we use in the grid. You have to remember, this is a key data. We use in the grid globally alternate current at 50 Hertz as a frequency. So please, everyone that studied this kind of subject should know that our grid work at 50 Hertz. Let's start with photovoltaic panel. As we have seen, PV module is composed of a number of solar cells connected in series or parallel. Solar cell is a diode. This is only a repetition. Okay, maybe I can finish with this. This is a repetition, and then we can have 5 minutes of break, as Erfan is suggesting. Erfan, thank you. So I finished this slide. The most used materials are polycrystalline, monocrystalline, amorphous silicon, another kind of material, but the market, I remember you, is full of polycrystalline and monocrystalline. The other solution are more case studies than actually market operation. Only in rare cases that are used cadmium, very rare. So if you have to remember, a PV module is made of silicon. That could be crystalline or amorphous. Amorphous is has a chemical structure like glass, just to let you know. Okay. We were discussing the components and the designing of photovoltaic systems. We have seen how photovoltaic panel is composed, and these are some of the values for the most common kind of panels. So a standard temperature condition that, I remember you, are an irradiance of 1000 watt per square meter and a temperature of 25 Celsius degree. Usually a cell has a power of 1 up to 4.4 watt, while a module with 60 cells has a nominal power of 255 to 265 watt, and a module with 96 cells achieve a nominal power of 330 to 36. So what's important to remember that usually a photovoltaic panel can achieve a power of between 200 300 watt. It is important in our world to have always in mind the order of magnitude. So if at the oral exam I'll ask you what's the typical value of power for a solar panel, if you answer me 200 watt, is it okay? Also, if it's not the exactly power output. But if you answer me, I don't know, 10 gigawatt, it is an important mistake, and I understand that you have not clear what is the power that a solar module can produce. Okay. A PV module is usually composed of a front glass with 3 to 4 millimeter thickness. What's the aim of a front glass? Is to protect the cell, okay, from, I don't know, the meteo condition, for example. Solar cell encapsulated by ethylene vinyl acetate that has waterproof properties, as I said before, to protect from rain. That for sure is the first thing that you can imagine can endanger the panels. A glass black sheet, aluminum frame, and a junction box. To obtain the proper cell connection, ribbons are welded to the main bus bars of the heat contact of the front side. So right now we are speaking of the connection that allow us to pass the current from the solar module to the circuit, so house or to the grid. Here I cited the interdigitated back contacts. That is the more common technology right now. So very efficient solar cell exhibit interdigitated back contacts, which simplify the connection and reduce the shading on the real side. But it's just to let you know, it's not the aim of the course to remember all the technicalities. It is all important that you understand how the components are working and the order of magnitude of power and energy that we can achieve with the system, and the potentiality for sure. Okay. Here, okay. There's an image with the bypass diodes that, as we have discussed before, are 2 or 3 for a group of 20-24 cell, are placed in the junction box, as well as the connection terminals. In case of failure, as we have discussed, bypass diodes behave as low resistances, and currently manufacturers offer watertight junction boxes from which 2 cables with plug-in connectors get out for an easy insertion. Okay, this is a more technical aspect. There's also a warranty. Manufacturer warranty is very important. Product workmanship, warranty for manufacturing and material defects, at least 2 years, usually 12 years, up to 25 years. So if you are interested in buying solar panels, you have the warranty that your solar panel has at least a lifetime of 20 years. Of course, with a reduction in the power because of the degradation of the cells, but this reduction has to be limited to 80% of the minimum power after 25 years, usually, and under standard temperature conditions. Sorry. Okay. The AV curve, as we have seen, of a PV generation is a copy at a larger scale of the AV curve of a single cell, whose conversion efficiency is independent of the power rating. So remember also that the conversion efficiency in the standard condition is independent of the power rating. So if a panel with a certain technology has 25% of efficiency, it is a good efficiency for a solar module, it does not depend on the power. With the technology, you can have 200, 300, 400 watt of power, but the efficiency is also always the same. It depends on the technology, not on the power. The PV generators operates with an input power independent of the load. It is characterized by maximum efficiency when the utilized power is maximum over temperature in open circuit. PV panels produce electric energy in continuous current, but our houses and the grid operates in alternate current at 50 Hz, as I said before. So we need a component that change continue current and alternate current. And this component is the inverter. There are 2 main kinds of inverters. Thyristors, that is an older technology, and we will not see it in details, and transistors that use nowadays in the context of the solar modules. Okay, maybe thyristors are used in other kind of technology, but we don't mind that. For our aim of this course, we will focus on transistor. The usage of transistors permits to transfer power from DC side to AC side in the absence of line voltage, self-commuted. The power transistors, 2 kinds mainly, MOSFET and IGBT, are switches. Closing and opening controlled will lead the LED angles in regard to a reference signal generated by the clock signal inside the converter. It is possible to produce reactive power, inductive or capacitive. Now, I don't know if you have a background in electric circuit. So if you are familiar with reactive power, inductive, and capacitive, but don't worry, it is not fundamental. I will explain you the main concept and the main difference, so you can understand also if you don't have technical background. So IGBT, insulated gate bipolar transistor, is more suitable if you are dealing with high voltages and high power output, lower switching frequencies, and tough environmental conditions. MOSFET, metal oxide semiconductor field effect transistor, is more suitable if your application operates under 600 volt, requires high frequency Rushing transformers and inductors, like in microinverters or USB chargers, or need maximum efficiency at light loads. As you can understand, for our aim, the IGBT is more suitable. Okay, so it is my interest that you remember that a solar system needs an inverter, that the kind of inverter that we use is a transistor, and most of the time it is a kind of IGBT. Okay, here are the difference. We will not waste time on that, because I understand that there's a technicality. So if you are particularly interested, you can contact me. I will explain to you better, but it's not the aim of this course. But it is the aim of this course to understand how the transistor work. The transistor on-off mode is in accordance with the pulse width modulation technique. What's that? A comparison is implemented between a triangular waveform generated by a quartz clock carrier and a sinusoidal waveform modulating. The carrier waveform has high frequency, while the modulating waveform has a power frequency. Control parameters are the modulation index, M, and the phase angle, beta. Now, if you see it, it's more easy to understand. This is a triangular waveform curve. Okay, so there are the off phase. So when the transistor is off, you can see that the line is below, while when it's on, the line goes up, and we only have two phases, on or off. There's nothing in between. Okay. The three examples that we have in this slide show us the case in which the transistor is on for 25% of the time, 50% of the time, and 70% of the time. But if we let the inverter work in this way, we will encounter failure, because we will have peak of power on and off. So we need to smooth this curve to achieve this kind of result. So from a triangular waveform to a sinusoidal waveform. That is called sinusoidal because of the same behavior of the sine function. Okay, so as you can see, the curve is smoother, is more smooth for sure. And this is done by the LC filtering. So the induction, you can see here, is the circuit. I know that if you have never seen anything before, it could be result difficult. But again, what is that I want that you remember? That the inverter works to change the direct current in alternate current. That the kind of inverter that we use is a transistors, and then the transistor use an LC filters to smooth the waveform. Okay, so this is the final result of the AC voltage. And this is the circuit that can module what the transistor done. So a simple AC circuit to control active and reactive power flow. The lead angle beta of the phasor V to ensure that the current phasor I is in phase with the voltage phasor. You can see in the triangle on the right, okay, that the voltage current is the sum of the voltage phasor, is the vectorial sum of the voltage phasor, and the induction. So the induction multiplied by the current. So if you see in the circuit, LD, induction, and RP are parasitic parameters. LD is chosen in the design stage. The active power is evaluated as voltage phasor multiplied by current multiplied by the cosine of the lead angle. What is the lead angle? The lead angle is the angle between the phasor of the current and the phasor of the voltage. So it is like a lead. I don't know if I can make it more clear than that. I don't know if I put an images of beta. No, I think there's only in triangular. But you have to understand that there should be the lower lead possible between the current coming from the solar module and the current that goes to the grid. And this lead is represented by the lead angle beta. Okay. So these are some characteristics of the inverter. Has a high conversion efficiency. So the efficiency is higher than 90%, from power from 10% to 100% of nominal power, and low no-load losses. Power factor higher than 0.9, and this is all technicalities. What you need to remember is the conversion of the inverter caused a certain amount of losses. It is low, because the efficiency from direct current to harnessed current is higher than 90%. And we also have the maximum power point tracker. I don't know if you remember when we discussed the IV curve, we have seen the power curve also. And the power curve as a maximum. To understand live what is this maximum and working in that condition, we need a maximum power point tracker. The maximum power point tracker is the combination of a DC-DC converter and a suitable control technique. The key components are transistor, in the same way as we have discussed before for inverter, freewheeling diodes, inductors, and capacitors. These are, sorry for that. Okay. Okay. These are different way in which we can, in which the maximum power point tracker can work, and the control technique is implemented in accordance with various algorithms. The maximum power point tracker that are more high in price use incremental conductance. It is the most correct method, which exploits the matching property of the load. load resistance equal to generator differential resistance. There is also another method, perturb and observe. It is the most used method and operates an increment or decrement of the voltage, checking where a power rise or decrease occurs. If an increase is observed, the algorithm continues to adjust the output voltage in the same direction. If a decrease is observed, the algorithm adjusts the voltage in the opposite direction. And last but not least, constant voltage. It is the least accurate method in which, after measurement of open circuit voltage, the proper fraction of open circuit voltage is imposed. What is it you have to remember? You have to remember that in our systems, we need a maximum power point tracker. That the solar module has a point that is called maximum power point, in which the power output is the highest. And for sure, there is different kind of maximum power point tracker. How I choose the better? It depends of our needs. Not always in design condition, it is convenient to invest in a higher technology maximum power point tracker, because I don't know, let's imagine that you need 100 megawatt of power produced by your solar modules. Okay, maybe a higher investment in maximum power point tracker could give you a 1% or 2% of energy output increase during a year. But to achieve this 1 or 2% energy output more, you have to invest like 10% more on your initial capital invest. You understand that it is not worth the money. Okay, so what that you have to understand, that sometimes in the engineering world, it is not always the highest technology solution, the better, but is the solution that is more suitable to our aim. Okay, so if I need to install solar modules in an house, I cannot allow to invest an incredible amount of money or in a big inverter on a high technology maximum power point tracker. But there are some cases in which it can be useful. So just to let you know, these are the three kinds of algorithms. I won't ask you that on your exam, for which of you that will try to obtain the exam certification. It is only important that you remember the maximum power point tracker. Okay, so we can pass on racking structure and design. During the design phase, it is important to focus on the geometry and orientation of the panels in order to maximize direct solar irradiation and mitigate inter-row shading between strings. So these are some of the parameters that you have to take in account when you are installing a solar module or different solar modules. The precise azimuth, quindi so true south orientation in the north hemisphere to capture peak solar radiation at noon. Tilt angle, inclination adjusted based on the site's geographic latitude to balance annual energy yield. Yield impact and seasonal adjustment, where applicable. Higher tilt in winter boosts production and facilitates snow shedding. Here we have an images, so you can understand what we are talking about. The main parameters are for sure the azimuth, because we need to have our solar module exposed to the sun for the most of the time during the day. As you can understand, energy production by solar panels has a strongly dependence of the solar time. Okay, so during the day we have high power production, high energy production, but in the night, zero or really low power production. But basing on how we put the solar modules, we can have more or less hour of exposure to the sun. So, basing on our location, our geographical location, it could be more convenient to apply a low tilt angle, beta, or a higher tilt angle. This difference is not only between summer and winter, but also basing on the place. For example, from where I'm from Italy, in the south, we have a lot of sun, so it makes more sense to have a lower tilt angle. So practically, basically, parallel to the roof of the houses, for example. While in countries like Norway or Sweden, they usually use higher tilt angle. So it is important to remember these two parameters, tilt angle and azimuth, and that you remember the difference between winter, or we can say cold places, and hot places. There are some way to analyze these parameters that we discussed. There are true pitch calculation. The spacing between modules rows must be calculated considering the shadow angle at the winter solstice. Incorrect pitch leads to the inter-row shading during winter peak hours, activating bypass diodes and drastically dropping string voltage. Of course, when you are installing different solar modules, you should avoid that the previous solar module make shadow on the other solar modules. Okay, so you need to have a precise distance from one solar module to one another. Okay. In the same way, 3D obstacle mapping, pre-installation shadow analysis using different software, identify parapets, trees, chimneys. Even partial shading on a single module can reduce wall string output by up to 50% in conventional system. What's the key point here? That I can make the best solar module with the best technology, the best solar cell, but if I put my solar module in front of a building that is higher than mine, I will have always shadow on the solar module. So the solar module is not useful. Okay. So when in the design phase, when you are installing your solar panel, you have to pay attention to the obstacle that could cause shadow on the solar modules, and to how the solar modules are installed, what distance, what angle, to avoid the shadow. Also, ventilation and temperatures play an important role. Heat dissipation. Maintain an obstructed air gap of at least 10 to 15 centimeters between the roof surface and the module, required to promote a chimney effect. With a temperature coefficient, Pmax, typically minus 0.35%, natural cooling yields up to 5 to 10% extra energy in summer months. It is the concept that we have discussed before when we talk about normal nocturnal operating conditions, and we talked about the wind velocity. That is a natural way of cooling the solar modules. So, in designing our project, we have to take in account also what kind of natural cooling forms we have in our disposal. Okay. It could seem not so important, but it can represent 5 to 10% extra energy in summer months. So it is important. Other aspects to take in account are integrity and maintenance, protecting against PID degradation, preventing soiling, and ensuring ergonomic inspection. After that, we have galvanic continuity and self-cleaning tilt. These are higher form of maintenance. So we should ensure a minimal tilt of at least 10 to 12 degrees to allow rainwater to wash away dust, sand, and droppings, reducing soil losses up to 8% annually. Of course, you can imagine if our solar module is full of dust, full of sand, their efficiency drop dramatically. Okay, so the biggest implants usually have a system of water that clean them. Okay, but instead for I don't know, buildings uses, so for the roofs of the building, it is non-convenient to install a system that cleans the solar modules. So to avoid that dust and sand remain on the solar panels, we can use a tilt angle a little bit higher. So, as always, it is a matter of what's more convenient and not what is optimal. Maybe in some cases, you make your calculation, your evaluation, and you understand that the tilt angle that is optimal is like 6 degrees, okay? But if you don't consider that at 6 degrees, the sand and the dust remain on the panels, at the end of the day, you will lose a lot of efficiency, okay? So you would prefer to have a little bit of losses because you don't have the optimal tilt angle from a sun point of view, but you achieve an overall higher efficiency with a worse tilt angle because you have taken in account the cleaning part. Okay. So at the exam, I could ask you what are the kind of losses in efficiency, and you have to remember that the cleaning part, other than the obstacle shadow or heat dissipation, play an important role. Okay, I hope that it is clear. To understand if a project has the chance to be financially convenient, it is necessary to perform an economic analysis taking into account energy productivity and net present value. Why we have done all this discourse about efficiency, about cleaning, about obstacles, about tilt angle? Because at the end of the day, to make a project, it has to be economically convenient. Because you can have the best project in the world, but if the investors understand that he will not have an economic return, you will not invest in your project. Okay, so these two parameters that we are analyzing are the most important, and are the first that you have to see to understand if a project is feasible or not. Here we have the equation for energy productivity, and it depends on global in plane irradiation, so the sun that arises on the panels, total area of the PV generator, so how much PV generator and what sources they had, rated efficiency of the PV modules, for sure, sum of power ratings of PV modules at standard temperature condition, number of equivalent solar hours per day month years. What is this data? Is how much time our panel is exposed to the sun. Okay, and performance ratio for a comparison of different PV system. This is another parameter like the fill factor that we discussed before. This is a parameter that we can use to compare different solar modules from different companies. Okay. So this is the first parameter to understand if our project is feasible or not. The second one, okay, so the first one was on the energetic point of view. The second one is purely economic, and this is the net present value. The net present value that is evaluated as minus installation cost plus the revenue. So the revenue is evaluated as the money that you could receive by the grid if you are connected to the grid, but we will see it later, or the money that you don't spend for pay the bills. I don't know if you previously were using gas, for example, or using anyway grid's energy, you pay a tot of money. You should make the difference with the energy that you receive from the solar module. So if in a day of 24 hours, for 8 hours, I use the energy coming from the solar modules, for sure, I can consider it revenue, the money that I don't pay to the bills as I was made before the installation of the solar modules. From the revenue, we have to subtract the operation and maintenance cost, that is the C in this slide. And we have to do this with respect to the real interest rate, usually 2 to 4%. This maybe could be the most complicated parameter to understand, the real interest rate. It is a rate that is used to understand how we can consider the future condition at the moment. So, for example, if in the next 10 years, I'm expecting that the energy cost will increase, like it's happening, for example, as you know better than me, because of the war, for sure, if I have installed the solar module, my revenue will be much higher, because nowadays, without the solar modules, I will pay a higher price for the energy. So usually, in normal condition, this rate is from 2 to 4%. But I think that nowadays, the companies that is evaluating their net present value use a real interest rate that is much higher, because nowadays the energy price is going up like crazy. Okay, so what's the point of the net present value? The net present value allows us to understand right now what's the value of our project, and this depends on the installation cost, so the capital that we put in the project at the beginning. It depends on the revenue, how much money we are receiving thanks to our project, the operation and maintenance cost, and the interest rate. There are some cases in which your country could reward you if you produce solar energy and give to the grid. Okay, this is strictly depends on the laws, so these are not physical or engineering factors. But there are some cases in which maybe you produce 5 kilowatt hours of energy and you only need 3. What about the other 2? If you are not connected to the grid, they are wasted. So you produce 5, but use only 3 kilowatt. But in some cases, you can sell this energy that you have produced to the country to the grid, and B, rewards will be paid. Okay, but we will see. Okay, we almost finished. There are 12 slides. So let's go to the next chapter, that is architectures. How we connect, convert, store, and distribute this power defines the system's architecture. There are three main architectures for a photovoltaic system: grid-tied, directly connected to the utility grid without batteries; standalone, completely independent, relies entirely on batteries and backup generators; hybrid, grid-tied plus storage, connected to the grid and features battery storage. Let's see the grid-tied kind of architecture. Grid-tied, directly connected to the utility grid, no batteries. How it works? The grid acts as a virtual battery. Overproduction, excess solar energy sent to the grid; underproduction, when the sun goes down, power is down from the grid. Okay, this is for sure the most safe configuration, because if you are installing your solar modules on your house, you will have need of energy for all the 24 hours of the day. But your solar panel produces energy only during sun time. So when the solar modules is in function, you use your energy. While if the solar modules in that moment is not producing anything, you can use the power from the grid. Okay. What are the pros? Lowest upfront cost. You don't need batteries. High efficiency and reliability. So in case of incident, you can always count on the grid. Reduce electricity bills and potential for passive income. So as we have discussed before, depending on the laws in your countries. Cons: no blackout protection. If the grid goes down, the solar system shuts down. Of course, if there's a blackout, you have not any form of independence. Okay, so you depend on the grid. Depending on the utility policy and netmatic rates. This is also another cons, because energy price and laws, fees, could modify during the year. So maybe you are expecting to have 30 years with a certain revenue, but this kind of revenue can change. So this is for sure a cons. Let's see the standalone architectures. The standalone architecture give you completely independent and relies entirely on batteries and backup generators. See, what's the difference? In the first case, you are connected to the grid. In the second case, you are not connected to the grid. So when the solar panel is not in function, you need energy storage, and you can store energy in the batteries. So it requires robust battery bank to provide power at night and during cloudy days; battery bank store excess DC power generating during the day; charge controller regulates the voltage and current coming from the solar panels to prevent battery overcharging; and a backup generator. Now, the standalone architecture is very rare. You can configure something like that if you are in a house alone, so not in a building, and is very risky, because as you know, solar panel is producing energy only for a certain amount of time, and if there are several days, one near the other, where you don't produce energy, you cannot charge your battery. So you have to pay high attention to this matter. It's different to see a standalone configuration. Most of the time, you have a grid-tied connection. Okay. Last but not least, we have an hybrid Grid-tied to storage. So you are connected to the grid and feed to this battery storage. How it works: self-consumption mode. You prioritize charging batteries and powering the home before sending excess to the grid. So you prefer to charge your battery rather than send your energy to the grid. Backup mode. During a blackout, the hybrid inverter isolates the home from the grid, idling, and powers essential loads using the batteries and the solar panels. Peak shaving. Discharges batteries during expensive peak utilities hours to save money. So, what are the pros here? Provides backup power during grid outages. Maximize self-consumption of solar energy. Protects against shifting utility policies. Cons: more expensive than basic grid-tied system, more complex installation and permitting, battery capacity limits what appliance can run during an outage. So, the hybrid architecture is, for sure, from a technical point of view, the best for you, but has very high capital costs. So, at the beginning, you put a big amount of money for the solar module and for the battery. Also, you need a series of permission. But again, this depends on your country laws. Okay, it's not the same for everyone. What is that I want that you remember? The three kind, let's say two kind of architecture: grid-tied and standalone, with their differences, and that from an economic point of view, it is important to understand how your country revenue you if you give energy to the grid. Because of that, you can consider to install battery, or if it is more convenient, to give and sell, so give to obtain a revenue, to sell the energy that you produce in advance to the grid. Ok, these are sub-architectures, quindi beyond the grid connection, PV architecture is defined by how panels are wired to the inverters. So these are little differences in the type of inverters. There could be central, only one big inverter, micro inverters, or power optimizers. Just a curiosity, just to let you know, it's not fundamental. String inverter architecture, panels are wired in a series, a string. Drawback: if one panel is shaded, the output of the whole strings drops. Microinverter, a small inverter is attached to every single panel. Advantage: panel operates independently. Shading on one doesn't affect the others. AC power runs straight off the roof. So we can choose between a single bigger inverter or many small inverters. How we can choose between the two solutions? Again, it depends on your project. It depends on how much of the time do you think that you can have a shadow, how much capital at the beginning you can invest, the power that you require. So different solution is really depends on your project. There is not a better solution absolutely. Okay, it depends on your project. And third is the DC power optimizers, a middle ground. DC power optimizers are attached to each panel. They don't convert DC to AC at the panel level, like in microinverters. Instead, they condition the DC power to maximize output, regardless of shading, then send it to a central string inverter. Offers panel level monitoring with slightly lower cost than full microinverters. This is a solution that combines the pros of the striking inverters and microinverters. And for sure, it could be a solution, but again, depends on your project. Just to let you know that this kind of solution exists. In this slide, we have emerging PV architectures. What's the meaning of emerging? That nowadays, there is not a big market for this kind of solution. They are studied. Maybe there could be some example of project, but there's there's no market side. Okay. We have building integrated photovoltaics, solar architect, where PV materials replace conventional building materials, solar roof tiles, solar windows. Agrivoltaics, collocating solar panels with agriculture. Panels are elevated to allow crops to grow or animals to graze underneath. And floating solar, to exploit the sun arriving in the ocean and the sea. Arrays built on fountains over reservoir or lakes, which saves land space and cools the panel for higher efficiency. Again, just curiosity, not market size projects. Okay, conclusion. We arrived at the end of our course. I hope I was clear. We will rapidly see pros and cons of the PV systems. So, from the pros, we for sure have that PV system produce renewable and clean energy, has low operating and low maintenance cost. You could be independent, as we have seen, depends on the architecture. Scalability. What's the meaning of scalability? You installing more solar modules can achieve higher power. Cons, we have high initial investment, intermittent production, space requirements, location dependency, and end-of-life challenges. Again, as you can see, as we have seen at the start of the course, this is a kind of technology that is growing and will grow in the years. Okay. I hope it is all clear. If you have any question, please ask me. I have the time right now to answer you. If you have some question later, you can contact me. I'll give you again the slide with my email where you can contact me. Yes, Amir. I read your question for everyone. Amir is asking, will you explain a bit about integration of PV panels and solar hydrogen production? Storage of energy as hydrogen instead of batteries. Okay, for sure. PV panels could be used to produce hydrogen. What's the problem of using hydrogen instead? Okay, I see another question. Okay, I'll answer first the first question. The hydrogen production. What's the problem? Hydrogen is an energy vector. So, of course, you can use to storage. But hydrogen production requires an important amount of energy. It's not easy to produce. It is not easy to store. Okay? Because hydrogen is to be stored in gas require a lot of space, and if you want to have in liquid phase, you have to achieve really low temperatures. So usually is not usually, I can say always, is not convenient to storage with hydrogen if you use your solar module in a house building or to use energy in that moment, in that place. If you have to use energy where you are, it is usually more convenient to use batteries. What's the point of hydrogen? Hydrogen is more convenient if you have to transport the energy. Okay? If you go to check the data, most of the hydrogen is produced by fossil fuels at the moment, just to increase our comprehension of how to produce and storage hydrogen. Okay, it is difficult to produce with solar modules because of the higher power that is needed. So, to answer your question, it is possible to produce hydrogen for sure, but it's more convenient if you have a larger plant, very large plant. You produce a lot of energy that you don't use, and you can storage in hydrogen and then transport this energy with the hydrogen form. But if you have to reuse this energy, like in the case of the building here in loco, it is more convenient batteries. I hope that that I answered your question. Okay, Shavin, I read your question, but first, Majid, in terms of architecture, did you draw any conclusion that which one works better in general? The one that works better in general is, of course, the hybrid configuration. Okay, because it's more it is suitable to different situations. Okay, if you have both the grid and the batteries, you could change your way to produce, consume, and storage energy in base of the situation. Okay, it could happen that 1 year is more convenient to use the grid energy with respect of yours, and one it is more convenient to sell the energy. Okay, or for example, also the time of use is important. Okay, so let's say that you have a battery. It can be the case that in your country at I don't know 10 p.m. It needs a certain amount of energy, and it pays you more than if you give you the energy in the grid at the 8 p.m. 8 p.m. or 8 a.m. in the morning. Okay, not all the time of the day is the same for energy price. There are moments in the day that we had some peaks, and in that moment the energy has a higher price. So if you can choose between batteries and grid, you have this advantage. So for sure it's better. What's the problem? The capital investment. If you are an investor, it is and you use the solar modules for this aim, is it a case? But if you want to use your solar module without taking in consideration all these factors, the most convenient way is the grid connection only, because the batteries cost a lot, and you can invest in that only if you have a knowledge and a precise project. Okay, so I hope that I have answered also that question. Now, the last question that I read, you mentioned that the modules have a power of between 200 and 400 watts for 60 or 90 cells modules. But now the modules that are commercially available from Tier 1 companies are between 650 and 750 watts. And I want to know if this is the case. You mentioned Europe or something else. Okay, you're right. You made a good point to underline that. I was talking about the more common solar modules. Okay, you're talking about Tier 1 that are also the more expensive. Please correct me if I'm wrong, but as I understand, see, for sure they exist, but they are not so common. Okay, so for again, it depends on your project. Maybe in the last building in China, they are using the Tier 1 panels that you mentioned correctly. But I don't know, here in Italy or in some other countries, maybe you should work on solar panels that was installed 10 years ago. Okay, it's very probably that you have the modules that we have discussed before. Okay, so I didn't say that the highest possible power achieved is 400. Okay, I was talking about the more common, just that. Okay, but it is true as you say that nowadays they are producing solar modules that have more power and also higher efficiency, because in the last year there was an important improving on efficiency from 22%, we're passing to 25, 26. Okay, yeah, this is true. If you have any other questions, please feel free to ask them.